if we look at this one here, this top chart, if you look whenever there's a number over a variable, right, it's in transformed form. We agree? So I could add a 0 to the back of this. Oops. And it would be in transformed form, correct? So my vertical asymptote is always my denominator anyways. Whether it's in transformed form or not, the vertical asymptote's the easy one. X is by itself, so x equals 0 would be my asymptote. Because I moved 0 to the nowhere, right? So my asymptote on a normal non-transformed function, vertical asymptote is going to be at x equals 0, horizontal asymptote is going to be at y equals 0. I moved 0 nowhere. So it's going to be x equals 0. I moved 0 nowhere up or down. So my horizontal is also going to be at y equals 0. We also use the rule that if your numerator is degree 0 and your denominator is degree anything not 0, it's always going to be y equals 0. Correct? Now my domain is just x such that x can't equal 0, XER. I'm just going to do set for all these. And then y such that y can't equal 0, YER. Now I'm going to go to the third one next. The third one is in transformed form. We have 6 over x minus 2 minus 3. And I have just the number over top. So my vertical asymptote is going to be x. I move 2 to the right. It's at x equals 0. I'm going to move 2 to the right, so it's going to be at x equals 2. And then x such that x can't equal 2. And then my vertical is at y equals 0, but I'm moving it 3 down, so it's dropping down to negative 3. So y equals negative 3. And then y such that y can't equal negative 3 YER. Grab this one. Oops, I kept going. Okay, the second one is not in transformed form, but when I have an x over an x, I can convert it transformed form, or I can just use the rules. So remember, converting to transformed form, I'm just going to show it up here. You didn't have to. You could have used coefficient of the fractions of the leading coefficients and gotten your answer just fine. But if we wanted it in transformed form, we went over, we could go 2x over x minus 7, and then we went plus negative 1 over x minus 7. We can split it up, correct? And then we have to figure out what can I add to this 2x so that the x minus 7's cancel off. So what would I add to it? A negative 14. And if I add a negative 14, then I'm going to actually have to add a positive 14 to this one. So I would get y equals to x minus 7 over x minus 7, and those cancel, plus 13 over x minus 7, and then I would get y equals 13 over x minus 7 plus 2. Now the only time you actually have to put it into that form is if I ask for transformations. If I just ask for asymptotes, I don't need to do that. Because my horizontal asymptote, I'll do my vertical first. My vertical asymptote is still just the denominator. So x equals 7. Well, here I moved it 7 to the right, so it'll still be x equals 7. And then x such that x can't equal 7, XER. Now, the other rule I said, if they're both degree 1, which these are both degree 1, I take their leading fraction of their leading coefficients for my y, right? So my y would equal 2. Oh, look what here. I moved it 2 up. It's the exact same answer. But I only need to convert it to that form if they ask me for transformations. I can just use a fraction of the leading coefficients when they're both degree 1 and say y equals 2 and not convert it at all. And then y such that y can't equal 2. I can only convert to transformed form if I have an x to the 1 something, x to the 1 something, or x to the 1 over x to the 1. That's the only time you can convert to transformed form. If it's an x squared, you cannot. All right? Which is chart 2. Chart 2, I gave you a whole bunch of x squareds. So the first one is an x squared over an x squared. So what's going to happen at most, you're going to have a point of discontinuity and a rational graph left over, right? Second one, I have a degree 2 over degree 2. Once again, rational graph with a point of discontinuity. Third one, I have a degree 2 over degree 1. So these are going to cancel off. I'm going to get a point of discontinuity in a line. So when these ones, you're going to have a rational left over. This one, you're just going to have a line left over. This would be a rational graph with asymptotes. This would be a line with the point of discontinuity. So let's go through and factor them and see what happens. So for this one, I'm going to get y equals x plus 5 over x plus 5, x plus 2. The moment that a factor cancels, I have a what? Point of discontinuity. It's at -5, and then how do I get the y? You substitute it back in here, and the moment you substitute it back in here, it's a standard of excellence question. Next is standard of excellence question in all of 30-1, just so you know. So we stick the -5 back in here, and I get -5 over -3, which is positive 5 over 3. Just sub it back in. Right? Now, what's left over? X over x plus 2. That is a rational graph, correct? So if a rational graph's left over, you have an asymptote vertical, and then you therefore have a horizontal. You can't just have a vertical alone. If you have a vertical, you have a horizontal. Always. So our vertical asymptote's always based off our denominator, x equals -2. Now we have degree 1 over degree 1. We have degree 1 over degree 1, we take a fraction of their leading coefficients, which is 1 over 1, correct? So my y equals 1. Before we do intercepts, we're going to look at domain and range. Domain and range is done the worst on all of these because people will forget either the asymptote or the point of discontinuity when stating it. So you have to remember you have two x's that it can't equal, the x of the point of discontinuity and the vertical asymptote, and you have two y's that it can't equal, the horizontal asymptote and the y of the point of discontinuity. So my domain is going to be x such that x can't equal the asymptote, so -2, and the x of the point of discontinuity, which is -5, XER. Most people remember both x's and then forget the y of the point of discontinuity is usually what happens. And then it's going to be y such that y can't equal my horizontal asymptote, which is 1, and the y of my point of discontinuity, 5/3. Because I'm going to have a dashed line through 1, and I'm going to have an open dot at 5/3. Right? So they're not going to, both of them aren't going to exist. YER. Now to get the y-intercept. Y-intercept, you just plug x equals 0 in. So if I go, do I need to have this version with these x plus 5s in it? No. I can plug it right into the simplified one. So I need, for my x-intercept, I'm going to do my y-intercept first. I need x equals 0. So I can plug it into the simplified one. So I'm going to get y equals 0 over 0 plus 2, which is 0. 0 divided by 2 is 0. So my y-intercept for this one is at 0, 0. Now my x-intercept, I need y equals 0. And I can plug it into my simplified version. So I can go 0 equals x over x plus 2. And then we multiply by x plus 2. And they cancel off. So I get 0 equals x. Remember I told you when we go to make an equation, so this one's at 0, 0 as well, which you would know because this one's 0, 0. But remember I told you when you go to make an equation off of a graph, which has a point of discontinuity, remember what did we always do? We went y equals a, we had that a, correct? Then we did a factor of the p of d. We worked the p of d back, and we had to do it on both the top and the bottom. So if x was equal to 2, we'd have x minus 2s here, correct? This was my vertical asymptote factor, and what was this always? My x-intercept. So once these are canceled off, the top always solves into your x-intercept when it's a degree 2. Always, always. P of D, x-intercept, vertical asymptote, solve for A. And remember, we couldn't use the x-intercept to solve for A. We had to use any other coordinate on the graph. So if we looked at the second one, when we factor it, we're going to get y equals x minus 3, x minus 4 over x minus 3, x plus 3. I wrote it backwards, and I'm not sure why. So those canceled off. So I know I have a point of discontinuity at 3 and something. How do I find that something? Well, I can plug it into the equation. So I get y equals 3 minus 4 over 3 plus 3, which is actually negative a sixth, right? You just plug it into the simplified version. Now what's left over? What kind of graph? A rational graph. So this is going to be a rational graph with an asymptote and an asymptote and an open dot, correct? And the rational graph that's left over is x minus 4 over x plus 3. So I'm going to go through, and I have a vertical asymptote at x equals negative 3, because it's what my denominator can't equal. If it did, it would be 0. And then once again, I have degree 1, so I take leading coefficients, which is 1 over 1, so y equals 1. Now my x-intercept, if it's degree 2, it's whatever's left up here, right? So if it's x minus 4, what's my x-intercept? 4 and 0. And how do I get my y-intercept? I plug 0 in for x. So into the simplified. So I'm going to go y equals 0 minus 4 over 0 plus 3, which is negative 4/3. So my y-intercept is at 0 and negative 4/3. You can always, whenever they ask for x and y-intercepts, y-intercept plug 0 in for x, x-intercept plug 0 in for y. That should be what pops into your head immediately. Now my domain is going to be everything but the asymptote and the point of discontinuity x's, and my range is going to be everything but the horizontal asymptote and the y of the point of discontinuity. So it's going to be x such that x can't equal negative 3 from the asymptote, and 3, which you could go plus or minus 3 and not put a comma in between. That would be absolutely fine. XCR. So you could have just written like this, plus or minus 3, instead of writing the comma. And then the range is going to be y such that y can't equal 1 because of the asymptote, and negative 1/6 because of the y of the point of discontinuity. There's no graph there. The last one I set you up for a little bit different. The last one, the denominator is going to completely cancel off when I get the point of discontinuity, and what's going to be left over is a line. So you literally have a line with an open dot. So do I have any asymptotes? No, because it's not a rational graph, it's a line. So when you get one of these ones, the third one, it's actually easier. You have no asymptotes. People do worse on this, but it's actually an easier question because it's literally a line with an open dot. So when we go to factor this one, we have to use decomp. 2x squared minus 5x. I don't remember what it was.
Plus 5x.
Plus 5x.
Minus 3. Over x.
Very good. 2x squared plus 6x minus 1x minus 3. Put a plus sign. Take a 2x out, we're left with x plus 3. Take a negative 1 out, we're left with x plus 3. And so we get 2x minus 1, x plus 3. That's my two factors. 2x minus 1, x plus 3. The x plus 3 cancel. So I know I have a point of discontinuity at negative 3 and something. How do I find it? I plug it into the what's left over. So 2 times negative 3 minus 1, which is negative 7. And what's left over? All right, so is that next period or period 3? That's period 3. That's period 3. We'll see what he does. All right, so we have y equals 2x minus 1. So it's a line at 2x minus 1, and it has an open dot at negative 3, negative 7. If you go to draw the line 2x minus 1, and you open the dot at negative 3, negative 7, and it doesn't land on the line, something is wrong. Your point is either wrong, or your line is drawn wrong, because it should be just a straight line with an open dot, right? The dot should appear on it. Now these are great, not applicables. I'm just going to write it like this because I'm lazy. You can't do that on a test. Okay, and then my domain and range are easy because it just can't equal those. Your x-intercept, it's a line, correct? you can find x-intercepts of the line y equals 2x minus 1. The y-intercept's easy. It's negative 1 because it's a line, right? It's your b at the end. So it's at 0 and negative 1. Your x-intercept, you're going to go 0 equals 2x minus 1. 1 equals 2x. Divide by 2. X equals a half. So it's a half and 0. Okay? Number 1 and 2 for radians. Oh my gosh, we just hit that into the trig part, but we're not there. 1 and 2 from radicals has to be done for tomorrow, and we're going to add a couple more. If you haven't gotten it done, I want you to do 1 and 2 for homework, just so we can get through them tomorrow as well. I'm going to get you to open up your notes to other functions. These I handed out to you already. So we're going to operations of functions, and after this we can start doing some calculus lessons sporadically throughout, because we'll have known all the information we need for that, for the first part of calculus. So here it says, and did you know that calculus can be done at the exact same time? It's actually a co-requisite with 30-1. I wouldn't recommend it, but it is a co-requisite, not a prerequisite. It's kind of scary when you do it as a co-requisite, but you can do it. Okay. So evaluate the following expression given the functions below and write the corresponding ordered pair. So we went over this already this year. If the number's in the bracket, what does it go in for? X. If it's g of x equals negative 13, what is g of x a fancy thing for? Y equals negative 13. Find x. That's all this is. So we're grade 10ing it right now. So, because you know we like grade 10. So here, if I want j of 2/3, I'm going to go to j of x, and I'm going to go 2 bracket 2/3 plus 7. Now this one gets done wrong because people don't put this over 1. If you put it over 1, people will make less mistakes. Because you do numerator times numerator, denominator times denominator. So we're going to get 4 over 3 plus 7. And if we want to add them, we need common denominators. So I'm going to multiply by 3. So I get 4 over 3 plus 21 over 3. And now I can add them because they have common denominator, 25 over 3. So function notation, that's all this is. This is a function notation for telling me 2/3 and 25 over 3, which we did in polynomials already, right? This is nothing new. 2/3, 25 over 3. Because we did polynomials first, this is way easier. We're literally going to look at E next. I don't know why it starts at D, but you're welcome. So g of x equals negative 13. So I go to the g of x formula, and I put negative 13 in for g of x. So I'm going to go negative 13 equals, and rewrite the rest of the equation, negative 5x minus 3. Then I just need to solve for x. So when I give you the g of x or the f of x, you have to solve for x. When I give you what's in the bracket, you put it in for x, and you're solving for y, technically, is all you're doing. So this is from grade 10. So we add 3, and you get negative 10 equals negative 5x. Divide by negative 5. X equals 2. And we're not going to do the rest because we did this in polynomials already, but I just want to remind you of what we did. So if it's in the bracket, it goes in for the x. If it's equal to, it goes in for the y, because it's what g of x is equal to. So we're going to go down here. Do you have a graph on yours? You have that, right? Okay. Sometimes it doesn't print the Cartesian plane on it. So these ones, we want to write them. What the heck is f of negative 1 equals 1? We talked about this. If this was a polynomial equation, we'd say that x plus 1 is not a factor of this, correct? If we go back to polynomials, this would be the factor would be x plus 1, and because it's not equal to 0, that would not be a factor of it. But we also talked about this just being a plain old coordinate, correct? What would the coordinate of this be? Negative 1 and 1. Because this is my x, and then what it's equal to is my y. So we go to plot that, negative 1 and 1. What's this one going to be? 2 and 7. So I go to 2 1, 2, 3, 4, 5, 6, 7. I'm not connecting them or anything, I'm just plotting the points. Then this one is 1 and negative 1. And then this one is 3, 0. If this was a polynomial function, I could say that x minus 3 is a factor of f of x. We're going back into polynomial zone. Now, is this a function? How do I check for functions? We've already done this in quadratics and polynomials. Vertical line test. For every x, there can only be one y. So for this x, negative 1, I have one y. For 1, I have one y. For 2, I have one y. For 3, I have one y. So if I drew vertical lines through each of these coordinates, it would only pass through once. Therefore, it passes the vertical line test. And so, yes, this is a function. Now we're going to flip. Okay, now I'm giving you a graph and asking for stuff. So if I go f of negative 4, what did I give you? The x, and I want the off of which graph? Off of f of x, not the g of x. This is why in grade 10 you're taught function notation, you have no idea why you are. It's for this moment in time. When we put more than one graph on a graph, right? On a Cartesian plane. So I go to negative 4. Here's negative 4, and then I want the f1. So I'm going to follow it down, and it is equal to what? Negative 2. G of 0. So I want where x is 0, but I'm going to follow it to the g graph this time. So what's my answer? 3. You guys answer the next ones. C, D, E, and F. So we have g of 3. So I go to 3 and y is 0. F of 3, I go to 3 and y is actually 5 on the f graph. And then x when g of x equals 0. So this is, I gave you what this time? Y. So I want when g of x is 0, which means y is 0. So y is 0 here and here. So my x is going to actually equal plus or minus 3. And then I have on the next one where f of x equals 0, which is here, because it's where y equals 0. So x equals negative 2. Okay? Sum and difference. So we're doing addition, subtraction, multiplication, and division for this day and tomorrow. So if I go h of x equals f of x plus g of x, what's my x's in all of these? Just x's, right? So I'm allowed to add them if I have the same x value. I'm allowed to add them if I have the exact same x value. So I have h of x equals f of x plus g of x. Graph and label each function, state the domain and range. Okay? We're going to do this without our calculators because if you can understand how to do these without your calculators, you'll ace every single question. Because it's not that bad. So we're going to go h of x equals f of x, which is square root x minus 4, plus g of x, which is plus 12. We agree?
Yes.
Okay. So, what is this? It's a radical function and it's been moved what? 12 to the up. Yes. And 4 to the right. 12 to the up and 4 to the right. Okay. So we know that we need to have it at starting at 4 and 12. We agree? Yeah? Do you remember that? Do you remember domain? Domain of a radical function is normally x is greater than or equal to 0 and y is greater than or equal to 0 is normally my range. We agree? This one has been moved 4 to the right, so it's actually going to be x such that x is greater than or equal to 4. Why did it not flip? Because there's no reflections. Now my range is going to be y such that y is greater than or equal to now 12, because why? There's no reflection. So I know I'm starting at 4 and 12. So would I go and just make myself a perfect Cartesian plane like that? No, I know I'm starting at 4 and 12. So I'm going to start here as my x-axis. You can start however you want. There's no lines on this one. And here's my y. There are no rules. And my y scale, I'm going to make be 4. All right. So I know I'm starting, and my x scale make be 1. So I know I'm starting at 4 and 12. So it's right here. Right? Because I go over 4, up 12, because I'm going up by a y scale of 4. How would I get my next one? I could plot the original 0, 0, 1, 1, 4, 2, 9, 3, right? And then just move that. Or I can literally make a t-table if I don't want to. So I'm at 4. I know my next one's going to be at 5. We agree? So this would be x, and then this would be h of x. So I would go square root 5 minus 4 plus 12, which is going to be square root of 1 plus 12, which is 13. So I'm at 5 and 13. Why didn't I pick negative 3? Or why didn't I pick 3 even? Because it starts at 4. If I put a 3 in, what I'm going to get under my square root? Negative 1. You can't have it happen, so it doesn't exist, right? You have to watch with radicals. So if I do 6, I'm going to get square root 6 minus 4 plus 12, which is square root 2 plus 12, which is something. 12, 13 point blah. So if I do 7 minus 4 plus 12, oh, that's root 3 plus 12. Still not pretty. 8. Oh, look at that. 8 minus 4 plus 12 equals square root of 4, which is 2 plus 12, which is 14. So I go till I can get nice ones. 5, 6, 7, 8, and 14. So it's going to be very shifty like that. Now, if you made your y scale be 2, it would be spread out further, right? In this case, you could have even let your y scale be 1 because it's not increasing super fast on your y's. So if you're like, if this was me and this was my diploma and I saw that I was squishing it ridiculously stupidly like this, I would go and erase it. I would make my y scale be 1 and I would draw it properly. I wouldn't be like, well, I'm committed. Put in the time. You have 6 hours. You're not committed. Trust me. The test is allotted to be done in 2.5. So then they gave an extra half an hour so that it could be done in 3. And then they were like, why not 6? So there's no time constraints on this thing. So we're going to look at these ones. Now h of x is 2 linear lines. So we're going to do h of x equals f of x plus g of x, which is what they told me about. So you would if it was subtraction, but you don't have to if it's addition. Because subtraction, you'd have to make sure you subtract the whole g of x function. So maybe you have to distribute the negative sign like in grade 10. But when it's addition and subtraction, you could actually go f of x plus g of x and g of x plus f of x. You get the same graph because it's the commutative property of addition. Same thing with multiplication. But a subtraction, you have to subtract the proper one behind it because it's going to subtract the whole function. Same with division, you have to make them in proper order. So here we're going to get 2x and 5x, which is 7x, plus 7 minus 11 is negative 4. So when I add 2 linear lines, I get a linear line, which makes sense. Okay? Let's go back to this graph back here for a second. So my original equation, we'll come back to this in a second. My original equation, one of them was root x minus 4 and the other one was 12. The graph of 12 is literally at 12, I have a horizontal line, right? This would be y equals 12. And then this one is a radical function and it's moved 4 to the right. So it's like this. We agree? When you add two functions, or you subtract two functions, they will only appear where their domain both exists. So if you look at the graph of y equals 12, the domain was x and element of the reals. It was the whole thing. We agree? But if we look at the square root x minus 4, it started at 4 and went on for life, correct? So where did both these graphs exist for domain-wise? At 4 or greater. So where did my domain actually exist on the combined function? At 4 or greater. So when you're adding functions, they can only exist where both functions exist. So here, my first function, it was at 4 or greater. My other one was XER. That's great. But I can only, the graph will exist where both of them exist. So the domain's actually really easy to find if one of them is restricted. If one of them is restricted, that will be your new domain because it's where it both exists. Now this one is a linear graph. This is a linear graph. So they're both negative infinity to infinity, correct? So their domain, the domain of this function, I don't even need to find it. I don't even need to graph this function. I don't even need to put them together. The domain of the combined addition function is going to be XER because they both exist everywhere. When I put them together, they're both going to exist everywhere. So the domain of adding and subtracting functions is really, really easy because you can just find the domain of both functions and it's where they both exist. So it's the most restricted domain part is where it's going to be. So if I go to sketch this one, this one has a slope of 7, which is kind of crazy. So I have a y-intercept at -4. And then I have a slope of up 7, right 1. I could do a t-table if I don't remember that. 1, 2, 3, 4, 5, 6, 7, and 1. I always do just a double over on it, but you don't have to. But I always just do, because then there's no assuming that anyone knows anything. I'm telling them exactly what it is. And that is not the straightest line. Pretend it's straight. Okay, the domain is x such that x and element of the reals, because it's a line, or negative infinity to infinity. And my range is y such that y is an element of the reals, or negative infinity to infinity for implementation. The least straight line I've ever seen. Scary. Okay, then flip over. Ah, we have a quadratic with a quadratic. What the heck happens there? Usually you'll get a quadratic, because a quadratic plus a quadratic, you're just collecting like terms, correct? The odd time when you collect like terms to the quadratic and a quadratic, or when you subtract like terms of the quadratic, the x squareds cancel off, and then you end up with a linear. So you do, it's not a guarantee. Like if your x squareds would cancel off, it would pop it to a linear equation, not a quadratic. So h of x equals f of x, which is x squared minus 3x minus 2, plus x squared minus x plus 5. Now quadratics have domain of what? Real numbers, right? So both of them have a domain as x and element of the reals. We agree? So where do both of them exist? Everywhere. So do I need to even figure out what the new graph is if they ask me for domain? Nope. Do I have to graph it if they ask me for domain of h of x? Nope. If they ask me for the domain, it's the easiest question ever. Find the domain of both, say where they both exist. So the domain of h of x is going to be x such that x and element of the reals. Because you can only, this graph can only exist where they both exist, and they both exist everywhere in domain. Range is not that easy. You'd actually have to graph the graph in order to find the range. So domain, you can say where they both exist, but range is not that easy. So if I go to do this, I'm going to get x squared and x squared is 2x squared minus 4x plus 3. But you could see that if I had an x squared and a negative x squared, they would cancel off, correct? And then I'd be left with a linear, so it's no guarantees. And then you can sketch that right from your calculator or whatever. I don't really care. We're going to move on. You don't just randomly like put a parabola somewhere.
Change the scale.
That sounds terrible. That's not a good idea. Just randomly put a thing and then just change your scale.
Yeah.
I don't think that would work. But the reasoning is okay. It's okay. All right, example 2. For each pair of functions, determine f of x minus g of x. Now you have to watch yourself with the minus sign, correct? If you have more than a monomial, so more than one term behind the minus sign, you have to distribute that baby in. And they will have every answer to you forgetting to distribute that in on every single subtraction one, every single time. So if you forget to distribute the minus sign through, you will get it wrong, and it will be there. And you'll be like, yes, I'm so smart. And then, but it's not. It's just that is what it is. But that's common error, so they'll have it. So we're going to go h of x equals f of x, which is 10, minus the absolute value of x plus 3. And to be honest, the absolute value graphs follow very similar characteristics to a quadratic. You learned about absolutes last year. Absolutes look a lot like a quadratic because they go 0, 0, 1, 1, negative 1, 1, and then it's like 2, 2, negative 2, 2, because your y values just become positive, correct? So you get something like this. So it's very similar to a quadratic in the fact that it's XER and your range is either greater than or equal to something or less than or equal to something if it flips. Ooh, if it flips, what's this? It's a flip. I can rewrite this as negative the absolute value of x plus 3 plus 10. We agree? So what does this negative in front do? It causes it to reflect in the x-axis, so it would make my range be less than or equal to whatever the heck my range is, correct? Is there a reflection in my x here? No. And if it did, it's like a quadratic. It literally just flips itself around and looks the same, right? And now I've moved 3 to the left and 10 up. We agree? So if I go 3 to the left, this is going to be very rough. This is going to be like Connor's sketch. And then 10 up, and then it flops, right? Look at how accurate that is. My domain of this one's still going to be XER, right? But my range is going to be y is less than or equal to 10. Okay? So you can use previous knowledge to figure these out. I didn't ask for domain and range at all. But I do know that this is an absolute value function, which means it's XER. And I do know that this is at 10. Let's pretend y equals 10, which is XER. So if both of them are XER, my graph is going to be XER, right? We do know that. Even with subtraction, same thing works. Addition and subtraction, your domain can be found just by where do both of them exist. So if we look at B, B is 2x minus 5 and x plus 8. Both of them are XER. We agree? So my domain as a combined function, whether it's addition or subtraction, will be XER, right? Didn't ask us that. It's asking us to just find h of x. H of x is f of x minus g of x. So I have to minus the whole of g of x, do I not? Not just the x. So you have to watch yourselves. Whenever there's more than a monomial behind as g, you have to distribute. So we're actually going to get 2x minus 5 minus x minus 8. And when we collect like terms, 2x minus x is x minus 13. They will have the answer to x plus 3. Absolutely they will. Because they're going to not distribute the minus sign through, keep it as an 8, and combine. They'll have that every single time. It will not be right. They'll have it there. Now, if it was an actual direct function, could you not check it out? Could you not type this minus this into your calculator and then see if you get this? Yeah, you can check it, right? Like you could type the original this in, type your answer into y2, and you should get the same graph, should you not? Problem is, if you don't put brackets on the original, you're not going to catch your error because it's going to give you the exact same. Okay, C, quadratic and a quadratic. A quadratic and a quadratic. Domain of a quadratic is XER. Domain of a quadratic is XER. So where do they both exist? XER. So I could say that h of x is going to be, domain is going to be XER. I can do that immediately. If I want anything more, I have to actually do work. But domain, I can just do really quickly. So h of x equals x squared plus x plus 8 minus 2x squared minus 3x. And I have to remember that I'm minusing everything that's behind the subtraction sign. So h of x equals x squared plus x plus 8 minus 2x squared, and then minus a minus 3 is actually plus. So I get x squared minus 2x squared is negative x squared. X plus 3x is plus 4x plus 8. Now, if I want the range, I literally have to get the equation, then I have to graph it and find out what the range is, right? Like, I can't get the range quickly like that. I actually have to do the work. Oh, g of x is x minus 2 squared. So they could give it like this. It could be like that and be done. And then you just find that. But more often than not, they'll actually expand it first, distribute, collect like terms. So I would, if I wouldn't even start it this way, I would expand this out myself first. So I'd go x minus 2 times x minus 2. Because when there's a squared, I literally just write them out twice so that I don't miss the middle term. If you don't write it out twice, most people will tell me it's x squared plus 4, which it's not. It's x squared minus 4x plus 4. So I always write it out twice so I don't miss that middle term. So I'm going to get x squared minus 2x is minus 4x. Negative 2 is positive 4. So I'm going to actually get h of x equals 4x minus 6 minus x squared minus 4x plus 4. And then I have to distribute my minus sign. 4x minus 6 minus x squared plus 4x minus 4. And I get h of x equals negative x squared plus 8x minus 10. Now, the other thing here is if you're given h of x equals f of x plus g of x, instead, which is the way I always want it, because I just take f of x and I add g of x to it, what they can do is they can write it like this. H of x equals f plus g of x. If they write it like this, I will rewrite it like this, because this form sucks, this form much better. So I write the much better, not sucky form. Okay? So in this one, I have h of x equals f minus g of x. Lovely, pretty, don't like it. So I rewrite it as h of x equals f of x minus g of x. They mean the exact same thing. This form confusing, this form nice. Yeah.
Why would they not put a third bracket? Because the g of x is like its own number. Why would they not do
Because this is just the same exact format of writing this. They can just write it in this form. It's f minus g of x. You can put the x to both of them. It's just another format. I don't like it, but you can give it to you. So the moment they give that to me, I rewrite it like this. And I'm like, yeah, thank you, but no thank you. I like my other form. Okay? So, I think you're all here now. So what I want you to do for homework is work through that hand-in I gave you. Because we're doing addition, subtraction, multiplication, division tomorrow of different functions. That's what we're going to finish up tomorrow. But I want that hand-in done. I want you to work through it. Now, if you don't complete it tonight, not a big deal, but we're going to go through it without you completing it, which is not as nearly as helpful to you as you trying it first than us going through it. So it's up to you. You're big kids now. You can make that decision. So you're going to work through that hand-in that I gave you as much as you can. If you can't get through it because it's in one night, it's fine, but I'm going to go through it anyways. Okay? So I'm going to give you today and tomorrow to finish it. We're going to go through it on Friday. That little hand-in booklet. The radicals and rationals. All right? I'm not checking it. If you don't do it, that's on you. Because if I just go through it and you haven't done it, it's not nearly as helpful as if you've tried it yourself. Okay?